大家好，我是王不老说半岛。Hi, folks. Today, I would like to continue my discussion about packaging process technology with a focus on the reliability aspect of packaging. And today, my focus will be so-called chip package interactions, CPI. And I have a few perspectives of my own I would like to discuss with you from the I would say from the integration perspective, some kind of a mindset and some kind of understanding, and that's what I like to bring uh, to the table for you. And today I would like to start with a talk with some interesting icebreakers. The first one will be the iPhone 15 Pro overheating issue. You know, some people are joking about it. It's just like your beautiful titanium cased I-15 uh, could pretty much put it off and could act out like a hot oven. And that's people have some complaints. The complaint was not that serious to call to make Apple uh, have a recall. That didn't happen. And however, some people believe that this is what they find out. It's not TSMC 3 nanometer fault. TSMC actually had a great party inside their own to celebrate their HBM high volume high volume manufacturing of 3 nanometer node, and they're very happy with it. However, that the later found out that there could be some problem in the design. One of the reason is the titanium case they put it on is super nice, super pretty. But unfortunately, titanium thermal conductivity is not that good. You know, this is data that dig it out. Titanium K thermal conductivity values is 17 watts per meter Kelvin. 17. If you look at the aluminum case, that's 210. All right. So this is like a more than one order of magnitude reduction in thermal conductivity. If you look at a cell phone, everything inside, you can imagine that, here you have a lot of heat generation. Eventually, it would come out. You know, eventually, the heat had to be absorbed by the casing, and then casing go to the air, right? No matter what you do inside. And the ideal world is that you should have a less heating problem. That'd be the nice. And so initially, it's complaining about maybe TSMC 3 nanometer. No, it's overheating because there's some BD control issues or some other issues. But it turns out not that. TSMC did a very good job in making their chip, 3 nanometer chip, very nice, low power, everything, and meet Apple spec. And so this is still ongoing. Let's see how it goes. But I think one of the key reasons the titanium frame could potentially be one of the problems. But my concern to the event is not because of material or system, right? My concern is that it, it's difficult for me to imagine that Apple did not know this from the get-go. They could just run once they assemble this product before they release it, they should go and do a bunch of tests, which I assume they must have done it. But why they didn't catch the problem? I think that is a big concern. All right. And then I mentioned here is this another lack of burn-in issue. I'll explain what burning is later on. And then I would like to introduce you the another interesting icebreaker. If you recall, the famous Samsung Galaxy Note 7 recall, the battery burned. Battery actually burned the heating issue so bad that actually it burned through the casing of the cell phone. I think that's, if you remember, that's about less than 10 years ago. That's what happened. All right. And let's look at a short recap of what happened.
Has a tendency to spontaneously catch fire. But it's only after months of investigating that Samsung is opening up about why the recalled phone was overheating. And it turns out it all comes down to poorly made batteries. Specifically, there were two separate battery defects, one in the original batch of Note 7s and another in the replacement units. To understand what exactly went wrong, you have to understand what's inside a lithium ion battery. It may look like just a thin square, but inside it resembles something like this snack cake. Thin layers of positive and negative electrodes are folded up like a jelly roll with a super thin separator, keeping the positive and negative layers from touching. If for any reason the folds aren't all just right and the layers get squished, or if they touch, boom, you got a short circuit and a phone on fire. According to Samsung, the original batteries were a bit squished in the upper right corner, and the tip of the negative layer curved over. Additionally, one of the ends was sitting in the wrong spot of the fold. The second set of replacement batteries suffered a different problem. These came from another supplier. And in the rush to pump out replacement batteries quickly, the manufacturer was sloppy and the separator was punctured, leaving the layers touching. In some cases, there was even some insulation missing inside. To solve the mystery of the exploding phones, Samsung created special facilities to test more than 200,000 phones and more than 30,000 batteries.
Yeah, you can see that this event cost Samsung a lot of money. Basically, people estimated it lost about $5.4 billion from this recall because every machine, I mean, every cell phone had to be recalled. And then to me, it is because they failed to perform this so-called burn-in properly. This is a this is a reliability step that they failed to do, right? And what is a burn-in? Before I introduce the burn-in, I would like to let us enjoy the nature's, the crudest burn-in, the most horrible burn-in that you have ever seen.
When any baby takes its first step. For species, that first step can be a doozy. I'm Jen Markham on Buzz 60. For an episode of its series Life Story, the BBC profiled the barnacle goose, a species native to Greenland, which nests in high cliffs to avoid predators. And because the geese only eat grass and the adults don't feed their young, the only way a chicken finds food is to make a daredevil 400-foot cliff dive off the nest. See, the little baby can't even yet, so it has to do a sort of parachute glide for as long as it can, and to land, it actually has to figure out how to balance on its fluffy belly from rock to rock, trying not to crack its skull open and not get eaten by a fox. Stops and is met by its proud parents. It's a staggering rite of passage that every goose makes, and while it looks deadly, enough chicks survive that the BBC reports Greenland's barnacle goose population has actually increased over the past 2 decades. I think Red Bull may have just found its new mascot, but
Yeah, this is how cruel the nature can be in make sure the barnacle goose can survive, can have a long, useful life of their own. And they screen out the weak babies with this cliff jump unbelievably. And this early failure, people now calling them, also calling them appropriately the infant mortality. So these two terms are interchangeable now. In our reliability world, we use this so-called belt bathtub. The bell, it's not bell shape. It's a bathtub curve. This reliability bathtub curve. It shows three distinct modes of how the failure rate of a product change over time. You have a startup phase, and then for some given reasons, you have very high failure rate always at the very beginning, right? Just like Samsung Galaxy Note 7. And that's what happened, right? When the product come out in a few weeks, people will find out, that the cell phone will catch fire. And how to resolve it is called a burn-in, right? You use burn-in to solve this problem. If they could solve this problem, and then the customer will see the extended useful life, like your warranty of your cell phone at least a year or 2 years from Costco, something like that, right? That's why any product manufacturer, we have to hide the problem, solve the problem. They don't actually hide it; they just weed it out. All right. Use burn-in. The burn-in means that they put the machine in hot conditions. Say they let it run some program on, turn it on, and let it run for a couple of days, and to see what happens. If Samsung did that for every phone before they sell it, of course they will find a problem. Just like Dell right now, if they want to sell you a laptop, they will definitely perform this process, this step first. Imagine if they didn't do that, then the customer will receive some defective, some percentage of customer will receive this defective product and will have returned it because it's under 30-day warranty, and then the shipping costs, everything costs, handling costs, Dell will lose all the money. And on top of that, you will lose their reputation to be, the number one in the world in making reliable PCs. And so this burn-in is a simple step to do. It just takes some time, but you just have to do it. And Samsung didn't do that. Why didn't do that then? Well, or even Apple didn't do that then. I think it's because I think they're rushed to get to the market. So they didn't do a thorough burn-in for their release, and that eventually come on and bite them. So this step is one that we definitely cannot ignore. All right. But by the way, in our packaging reliabilities, we have to exclude this one out. We have to make our packaging avoid this problem from the get-go. You must screen your process, your product very nicely. So everything you do, you try to improve the reliability and the useful life of your product is focusing on this part. Okay, you want to push these wear out barriers as far as I can see. All right, and this is what your goal is. Okay, and let's come back and look at what Samsung did to improve Note 7 reliability. They have this so-called 8-point battery check. They check this, check that, X-ray check, visual check. All these things take, a lot of time. And of course, they have durability tests, kind of like a burn-in test. Everything they do, try to ensure that there's no problem. But to me, I did not see a root cause fix with the new design. All right. What I meant is that if you recall in the video, they say there's something here, the sum of the wire at the corner is squished, all right, and it shouldn't happen. But did they figure out a new design to make sure it will be squash proof to improve? So even there's some deformation at the wire, they still can handle it. I didn't see a root cause fix for that problem, right? So I think that's my comment for that. So that's my perspective. I don't want to see too many tests. I want to see some root cause fix. I think, but that's basically that's my mindset about this. Now let's finish our icebreaker and coming to our packaging reliability. And the key factors affecting the packaging reliabilities, I could categorize into 3 categories. The first category is that the early failure must be ruled out before focusing on CPI warehouse. The so-called CPI is the chip package interactions. The reason it's the most important one is because you put many different different chips, packaging material. They are all heterogeneously trying to integrate into a package. And each one of them had carried non-uniform heat generations. And each of them could have different tolerance and have a different CTE, the coefficient of thermal expansion. So because they're different material, that by nature, they just behave differently against the temperature being created, right? So you could have layout issues, right? Warpage issues, all these issues, these are all because they all intertwine, okay, interactions. These interactions react among themselves. So it's hard to decipher, hard to tell the difference, therefore hard to fix. And so this is what I try to focus on today. And as far as the external factors, because packaging is where the chip gonna meet the environment. It's like humidity, right? The ionic contaminations. Where you gonna put your chip package? Is it for car? Is it for space shuttle? Is it for missile? Something like that, right? The temperature of your package. All this, and then even in outer space, the solar winds, radiation. This gives you the spec that you need to meet. This is related to the spec that related to the packaging's goal. All right. And then this is the internal to package and then against the specs set by the environments. Right. Go a little bit deeper is that my perspective on CPI is that basically the chip package interaction reduce the reliability margin. It kind of narrow down your process margin and your reliability margin due to the variability. The reason is that each component they need to be understood in terms of variability against the other one because you're sitting right next to it. You have a neighbor who has a different personality, and then you live in an area that the whole area had to behave according to spec. So this variability includes the thermal issues, right? The thermal issues, if you're a logic die, then you heat up tremendously. And DRAM could also heat up too, because they have the logic periphery. If you don't do a good job, they probably still have some thermal issues. And the layout, where are you going to put them? How far apart are you going to put between themselves? And then CTE difference, right? That these are all important thermal issues. And we could see that the layout issue or the configuration issue, we could see that from the I-15, which I saw, right? The mechanical issue is the warpage, and then it could, because of thermal expansion, you have a different CTE, right? So normally your packaging will have a problem with imbalance. You create thermal stress, and then eventually it will cause a warpage if that issue is not resolved. And the problem with the warpage is the potential incomplete and weak interconnects. So when you want to bond something, if they are warped, then you cannot do a bonding properly, right? Like a micro bond. And so that we're gonna see that example later on. And then the particles. So right now, everything you do, you have to dice singulation. You have to cut the die from the wafer. You cut, and you have to you clean, you polish, you debond, and then you etch. Everything you do to the wafer and to package, you have some particle generated. And how to, first of all, reduce the number of particles generated. Second of all, how to clean them. That's not an easy thing to do. And lastly, but not the least, electrical noise. Your neighbor, maybe you're a large guy, you run very high frequency, and your neighbor maybe cannot tolerate this frequency, generated some kind of electrical noise, some kind of RF that will affect them, right? So you have to watch out that first. Do you need to put some kind of shielding around it? I don't know. So this thing is difficult to test. You have to be very careful with it. The mechanical, the warpage is very easy to see. When you make it, you find out, oh, it warped. You over your spec. Your spec may be 5 to 6 mil, and then you have warpage that over 10 mil, then you're in trouble, right? So all these are easy to see. This is rather easy to see. And then particle are harder to see, but because your packaging scaling, we are going to denser and denser HBI, the hybrid bonding interconnect. The pitch are so small. So imagine if a particle that sits on top of the bonding interface, then you ruin it, right? So the particle definitely plays a key role. So at the end of the day, what does this mean? That to the tool vendors, they need to bring the tool to meet back-end line specs. This especially related to the particle, okay, on top of all the other stuff. Because when they have, in the old times, for the old package, because the pitch is large, couple of microns, like 10, 20 microns in some cases. So any particle is usually much smaller than that. You don't really care. So you did not focus on your development to reduce particles because they are tolerable. But right now, with the packaging advancements, you're going to below micron now. The goal is to below micron. And then so any particle size larger than micron is not allowed. This means that you're going to make your tool look like a semiconductor, the front end manufacturing part, which is the closest one will be the back end of line, the copper fill, and then the CMP. That kind of tool spec you have to meet now. You have to modify your tool to be more semi-manufacturing like. You cannot, your clean room will be different, right? You cannot have a dirty clean room. Your clean room spec will be different now. So all these come with a cost, So let's come back to our famous reliability improvement, the reliability bathtub curve. I'd like to re-emphasize again that focus is on reducing CPI impact. We studied this because we want to extend this useful life as much as we can. And then by understanding the way our failures, why they will failure gradually and then why they start. If we figure a way to fix this problem by pushing this line further down, we could really enjoy a higher useful life or a harsher environment. Okay, and so I would say pushing the useful life envelope as far as you can, pushing this partition, push it as far as you can. Okay, that would be the goal. There are certain features, certain interesting things about packaging. And let's look at the TSMC, one of the report is sent out. That's very interesting. Packaging yield needs to be 95 to 100%. It's not like if you go to TSMC and say, I want to buy a 3 nanometer chip and what yield you could provide me. They would say, oh, my 3 nanometer is pretty good. It's about 80, 90%. All right. And if you ask, oh, I want 100%. I said, no, that's not possible. Okay. That's going to work. And then I will give you 80, 90%. That's probably the best, theoretically best you can do. Right? It's not like I could do 100%, but I did it. So I do it because I want to make it fast and cheap. So I give you 80, 90%. No, that does not work that way because the particle sitting on a wafer to have a yield impact is purely a random effect. It's a part of the Poisson distributions. And then you cannot have 100% yield. But you look at their packaging, they could have 100% yield. And then it's against the common sense that the larger the die, the lower the yield. That's common sense for the silicon chip world. The larger the die, you have a lower the yield, like FPGA, right? FPGA could have such a big this is the die size map. Okay, semiconductor die size. The die size of FPGA or high performance chip, computation chip, it will be much lower. Okay, this yield of 100 millimeter will be much higher than the 800 millimeter. Assume all the manufacturing process are very, very similar. Okay, that is because the Poisson ratio, Poisson statistics And then I have discussed that extensively in my talk in first and second in my series. If come back to this talk, to this CPI, you could see that they could easily achieve pretty high yield. Well, I said not easily. They did a lot of job on that, right? They're number one in the world. They achieve high yield for the 91 millimeter square. And then a larger package, they could achieve 100% yield. It's 100 millimeter square. This trend is not happening in the traditional silicon chip world. And the reason they want that to happen, one of the key reasons is the high sunk cost of the non-good die. All these KGD non-good dies, because all these dies, before you put it on, they already come from a semiconductor fab. It costs a lot of money to make. So be very careful. Any one of them fail in the package, the whole package failed. Imagine that the cost, the sunk cost associated with it, right? And then, so this is one of the features that I observed, that I've seen from the package, or the package technology. So the key feature that I summarized for you is that chip on package are 100% non-good dies. They have to be 100% non-good die. You cannot put a bad one here and expect everything else to work after you assembled it, right? So your requirement is much harder than regular chip, much harsher than regular chip. Packaging is like assembling a machine of all good dies. It's just like your washing machine, pretty much. Right? You take all the good parts and you put it together and hope that the machine will work. And of course, you have design, you have put everything together, you have tested, and make sure that the machine is working. In the CPI, in this packaging world, you can see that you can lose from this paper, from this picture, the interposer, right, for the CoWoS process, chip on wafer on substrate. That's the one that makes TSMC world number one in terms of packaging. You can look at the HBM, the memory, it is sitting right next to the heat generation logic chip. All these are different material. This is DRAM, and this is logic. Of course, they are all silicon to most of them, and they put on top as interposer. The interposer could be many material. It could be silicon, it could be organic, it could be a piece of glass. Right? So all these are heterogeneous integration. They are all different, and they have different behaviors. And the bottom at the end of the day is could be product dependent. Right. So the AMD's packaging is different from the NVIDIA's packaging to a large extent because they are different design. So when the foundry provides service to them, they have to work with them a year or two before they mature the technology. Everybody has different concerns because each chip could run with different, say, different clock speed, right? And then or different temperatures, and that will affect everything. The issue is that since it's product dependent, and so it's costly to fix for large or complex packaging. So if a problem find out, first of all, it's not easy to find where the problem comes from. Second of all, if you find it, fix it, it's not an easy job too. And therefore, fewer and fewer foundry can afford to do advanced packaging because simply the cost is too high. Imagine if you want to put 3 nanometer here, each 3 nanometer costs you pretty hefty couple $100 already. Now you put this the DRAM here, and then you put everything together. Imagine who can afford to do that, right? So that's a concern. Come back to our die yield versus packaging yield. A die yield, as I mentioned before, the particles are random with a Poisson distribution. So it's not possible to yield 100%. The larger the die, smaller the yield. That is what we know from classical yield theory. Easy to find out this is the case. We've been learning this for the last 20, 30 years. But packaging yield a little bit different. Their dies are all good dies. They should have only systematic errors, all right? And here you have the random error. the random kind of Poisson distributions. So this part you cannot remove. All right. The random error, you could reduce it, but never be able to completely remove it. But in packaging, you may have some random error, maybe, may or may not be, but your big one is systematic error. This one you will call the CPI wear out. They start to deteriorate, right? But the 100% yield at the beginning is possible, all right? So in this lifetime, you could have 100% yield. Okay, that's no problem. Of course, as I mentioned before, you had to remove this first. This one had to remove first. So the next question is, will CPI depend upon die size? That's a good question. I think nobody knows the answers unless you really have the data. You can see that the different chips, right? They from the 0.1 millimeter all the way to 800 millimeter. As I mentioned before, the world's largest die is 558 millimeter. That's the reticle size, field size of a reticle. You cannot have anything bigger than that unless you do something crazy, right? Like side stitching, something like that. Other than that, the largest die you could produce is 800, something like 800. And if you put this into a package like AI package, like NVIDIA A100 or H100, and the reliability concern, but compared with a laser chip, could be very different, right? And here is much costly, and here is much cheaper. So the tolerance will be completely different. The spec will be different. I think that's my point. So you always have CPIs for sure, but whether CPI going to impact your spec, that's a different story, right? So what do we do then? I think I would recommend we go into reliability spec. Right, this spec is a good start. Industry and semi, we call it semi. Okay, we have all kinds of specs that you have to meet, and reliability spec is one of them. But I think it's a necessary but not sufficient, a bare minimum. This one you should go and as a start, at least you need to meet the spec. What kind of spec you have? You have high temperature reverse bias, thermal cycling, shock test, high temperature and humidity, haze test, mechanical stress test, drop test. All these kind of tests are very important for you to meet. But that doesn't mean that they are the only criteria you worry about, right? And the place we go is called JDAC. Usually we go here. These are popular one that I'd like to share with you. That JDAC, all right, you go into this website and then you type in your spec or you do a search by what kind of spec you want. And here I find out that JP148B is the one related to what I would like to have as a beginning, is a reliability qualification spec for semiconductor devices based on the physics of failure, risk, and opportunity assessment. So if I click that, so this one search, this one will find, right? And that's the spec that you could go and study and download. You need to log in and register, and you could download for free, right? Then with that, I think the spec, what is the purpose of spec? It's a spec is the industry collect all the data they could find, and then the databases, and then want to help you to be able to design for manufacturing reliability to complete this called DFR and BIR, right? Design for reliability and building reliability. So hopefully with this mindset that you could produce your product in a better way to meet these criteria. So this is the goal of a spec. But in reality, they just say this is one you need to meet minimum and minimum. Okay. And so this is where I suggest you as a good start. And then let's look at the CPI some interesting thing we could find online. Here, I like this picture because yeah, the smiling face and the frowning or the sad face, which one is better for CPI related warpage? You have put your devices on top of it, on top of package, and then you find out that your package has some warpage, and you have two type of warpage. Which one you prefer? Or which one is, of course, you don't want either of them to happen. But if it happens, which one is a little bit better? The smile face or sad face? It turns out that the smiling face is no good. This one, it's okay. It's not too bad, unless as long as it's uh, not too bad. If you have the same degree of warpage, then frowning convex is what you like to have. This is actually the same as a CMD of a wafer. They prefer compressive. They prefer compressive stress than tensile stress because tensile stress will crack. And here, with a smiling face, the weak joint will be here. When the solar ball was touching the other solar ball here, right? The smiling face will have a larger mismatch here. As far as the convex face, here will be less. If you have another solar ball on the other side, you want to solve these 2 points. The frowning convex warpage will have less mismatch to worry about. So smiling face at the end of the day is not as good as the frowning face. Let's view CPI from another perspective. I call it a statistical distribution perspective. What I mean by that is that let's look at these pictures. The component A, not product A, actually the component A is fast grading, and then the component B in my wording is slow degrading. All right. If you pull these two together, then at the end of the day, you have a product that is you have a overall distribution broadened. The distribution broadened. It was tight in the beginning. These are tight. Okay, this one is very tight, and this one a little bit broader. Okay, and this one has fast grading. At the end of the day, you follow the statistical rule, then your sigma is much larger than the two combined in following the square root law. Okay, so imagine that in your package, a failing part inside of the system will broaden the resulting overall distribution. And that's what's happening in a statistical sense. And I will explain this in detail in the appendix in terms of the reliability statistics, the whiteboard distribution. In this talk, let's just focus on some interesting phenomena. If you recall, I have discussed in the early pages about the yield. Okay, the yield here, this package that TSMC is working on, the system on integrated substrates, SOIS or SOIC. Currently, it's SOIC. This is what they did for this specific case, SOIS. And I mentioned that the yield, for the larger die, they achieve 100% yield. But how do they did that? What's a major design here that they saw the warpage problem? They put a stiffener ring, okay, meaning that they're afraid it's going to bend. Is the warpage here is probably not good, So they put a ring, a guard ring, around the package in a way so as that they don't warp, right? This is a ring, and so in that, of course, that worked, right, for them. And then if you have the same problem now, my challenge is for you is that, what about glass substrate, right? This is what Applied just announced recently, that they work with a supplier called Epsilix to create this glass substrate for packaging, right? It's for Intel packaging, glass substrate technology. They want to get Intel business. They try to convince Intel that the glass substrate is good for the future. Well, glass substrate does have a lot of advantages, right? It has, I think, the key advantage. These two are the key advantage. The zero moisture absorption. It's a kind of hydrophilic. It doesn't really like water. If you have done some surface treatment right, it's not a metal or semiconductor. It's a ceramic. So basically, they don't have a dangling bar on top, and so the moisture absorption is less, much less. Right? It's not exactly zero, but it's much less. And then the very high chemical resistance. So that benefits your process. And then the CTE or SiO2 is much less, about 20 to 25% of silicon only. So it was less sensitive to temperature variation. Yes, fair. So the coefficient of thermal expansion of SiO2, of course, much less. That's benefit too. So they don't warp that easily. And thin core. Thin core, I'm not sure is a kind of advantage or not because silicon can do the same thing, right? Because you're comparing two silicons. And they say they are thermally and mechanically stable. I have that claim. I have a little problem. This is what they claim. Right? From the thermal and mechanical stable perspective, silicon has a better Young's modulus and 100 better in terms of thermal conductivity. So I don't see they can stand on that. I think because the thermal expansion has the give you potential lower voltage, but you have a thermal conductivity problem at the same time, right? Heat need to conduct away. Unless you've done optimization, your heat transfer property is not as good as silicon, even though silicon has has a little bit not as good thermal the coefficient of thermal expansion. So these are intertwined problem. You can see that now. And of course, this is the surface flatness. And this is good, but silicon is not that bad either. All right. So I would say that this one is indeed the best. Okay. The rest one is case by case. So I would argue that what about the disadvantages? How about the cost? This is going to be cost you. It costs you more than silicon, I'm sure. And then thermal conductivity, and then the integration process maturity. This substrate is not that new, right? People learn, still working on it. And I'm sure TSMC is working on it too. And these big guys are working on this new substrate, but currently there's still POR, still silicon, that give you the best overall performance. So let's come back to this the picture we introduced. So if I challenge you by say I'm going to remove this ring by putting this on top of the glass, then my form factor will be this only, will be much smaller, right? I don't need stiffener ring anymore. I put everything on top of a glass substrate, so I could build my package in a much smaller size, right? So, yeah, that will be advantage. So this means that the old design will be impacted by the new material introductions. This rewrites your CPI. Your chip package interaction are different now. You're dealing with glass. It's more costly, but at the same time, you have a smaller area. Right? And the whole thing changed. You have to redo the whole design to see whether you could use the glass, this new material. Right? So things are evolving and changing as we speak. Okay. Let's do another learn. Let's use this Nexperia packaging and then see what can we learn from that. This is an interesting product. Let's check on what it can do.
The success story from the leading innovator in package technology, Nexperia's CFP15B, is a future-proof, robust package delivering high power density and the lowest profile on the market.
I want you to focus on their copper structures, where they will show you later on. To this, obviously, to me, they reduce their CPI issues, the warpage and thermal issue. pretty good. Just so pay attention to the copper constructions.
The CFP-15B is engineered for maximum robustness and reliability under the toughest conditions, making it ideal for automotive applications such as engine and transmission control units and safety applications including braking systems. This reliability was proven when the CFP-15B passed board-level reliability compliance at a leading Tier 1 automotive supplier. It was confirmed that CFP-15B exceeded twice the level of reliability performance that would be expected with AEC Q101. Furthermore, power temperature cycles combining temperature cycling and intermittent operating life tests saw the device achieve a qualification of 2,600.
You can see the heat conduction plate, they put it on, and then the rigidity, I mean, the overall strength of their supporting pins to make sure that the chip inside does not have a thermal problem, it does not have a mechanical problem.
Goals. All of this is made possible by key design innovations and the use of the highest quality materials. The CFP-15B also provides zero delamination in the areas around the leads, die, and clip, eliminating moisture ingress and increasing performance reliability. The solid copper clip reduces thermal resistance and optimizes the transfer of heat into the PCB, allowing for compact PCB designs. With its superior thermal performance and space-saving opportunities, the CFP-15B is an ideal replacement for SMX and DPAT packages. Additionally, its versatile package design means the CFP-15B can be integrated into a diverse portfolio of products. This package offers single and dual configurations and is used in different power diode technologies, such as Schottky and recovery rectifiers, and can also be extended to transistors. Connect and find out how your design can benefit from Nexperia's CFP-15.
Yes, you can see that the copper packaging, of course, design and solve their warpage and thermal issues. I hope that we can learn something from it. This is kind of a big one, and the copper plate is so large, and then the chip is a medium-sized chip, and then the copper help them to get the heat out, and then that works for them. But what about us? What about the thing we do like this? This is the 3D stack that the HBM on top of logic die and on top of interposers. What do you think about these configurations? And to me, this configuration is a pure nightmare, right? Because this HBM, you want the HBM benefit. It gives you a huge benefit in terms of bandwidth. You can stack, many DRAM inside, right? People stack 12, 16, I don't know, the sky's the limit probably, but you can stack a lot of memory here and then bond them together with a TSV. And then here it could be microbond, or in the future will be HBI, the hybrid bonding. And then they put it on top of logic die. Well, that's a bad idea. Why is that a bad idea? Because DRAM is very sensitive to temperature. It will start to stop at 85 degrees Celsius and fully absent-minded in 125. So, and logic, how hot they run? They could run 100 degrees Celsius easily. All right, these modern days die run pretty hot. Okay, pretty hot. And currently, if you look at advanced packaging, each packaging run about 600 watts to 1,000 watts now. It's terrible, right? So these configurations is really a bad idea, right? This is what you want because you put HBM on top logic die, the form factor is smaller. Things can be compact, but from the heat transfer perspective, that's not a good idea. So what can we do? Well, it's not what can we do. Let's look at what Intel did. Okay, if we look at their fabulous, right? They have a physical separation between the computer chip and the memory, right? The microbomb TSV, they could always replace it with the HBI, the hybrid bond, right? So there's ignore that. But the physical separation is important, right, for their package because the heat is going to conduct their way to here, all right, or to top, all right. They did not put the memory on top of the chip yet. This will be ideal case, right? This will be the ideal case. They put the DRAM on top of logic directly. That'd be nice. So what I meant is the physical separation between the hot CPU and the cold, or not that cold, but preferred to be cold HBM is important. This is important. And what about AMD? Well, they're the same. Now look at this. This is the logic die, there's logic die or memory die. They didn't stack them either. I didn't stack them either. They always put it side by side. They have problem with putting on top because these are all probably all chip designed for server. They are running on very high power, right? They want very large current, so they could do very fast computations. Yeah, it's just like Intel. They put the chips side by side. They did not stack the HBM on top of logic yet. Probably in the future, but that will be enabled by TSMC, right? If you look at TSMC recent publications, these last year publications in TD, you can look at this is the old generation of SOIC edge horizontal. You look at this is the logic die, and then they have a physical separation against their memory cube. That is the HBM we're talking about. And then the new generation did not change the configuration. They changed only one thing, maybe a few things. They changed the microbond to HBI. That's pretty much what they do. And then you could see the benefit of the HBI, the hybrid bonding interconnect, or direct copper bonding. The distance, the size, overall size is smaller now because they could thinning it down and have copper interconnect. So this reduced the RC pretty good. The capacitance also benefit. Everything benefit. And they probably put a cooling. I would imagine they put a cooling cube on top to cool the things, and then also the logic, the same thing. And everything used to be micro bomb returned to HBI bomb, right? And still no HBM on logic direct. Maybe in the future, but not now, right? Because they still want to avoid the heat generation, the temperature going higher here, and then this is very sensitive memory. They had to be as far as possible, but within the form factor. So this is they call system technology co-optimization is a STICO. It's a STICO. Okay, I would say that's their SOIC strategy, and this strategy is enabled by the copper bonding. That's the current what's the most advanced packaging, and you can imagine that to do an experiment on this is hard. It's very hard, because you had to make sure everything runs at certain temperature and certain configuration. Currently, you could run pretty much on software. It's difficult to do it on hardware, right? Because hardware want to make everything work 100% yield before you can even test it. So that's a hard one. And each tape out will probably take you 3 months to 6 months or a year to complete the cycle. So it's not an easy thing to do. Okay. So the bottom line is understanding CPI is getting harder and harder on my amigos. The packaging scaling, the form factor reductions, make everything dense. And you can see all these crazy parts sitting right next to it. In the future, people are talking about integrating, say, 3-5 chip, like a arsenide chip, all kinds of chip, germanium chip, all into one package. And each come with different heat issues and different coefficient of thermal expansion. All these meaning that your CPI will be exacerbated. That's not good news for you. But it's still one thing that's for certain. The design to get the heat out is a fundamental. How do you get the heat out? We discussed that in a previous talk about this as well. So everything, the origin of the devil is the heat. So that part we really need to focus on. Okay, and this is my thought on the CPI. And before I let you go, I think at the end of the day is we need to have this mindset. You need to design for reliability. Okay, you need to build in reliability, which means that when you have a design, hopefully it will be foolproof, right? You could easily weed out the so-called you easily weed out the early failure issues with a good design as a start, and then you want to push the envelope as far as you can based on the spec of your that's set by the external factors, right? The environments that your package is going to be worked on. Okay, so I will leave you that. Of course, at the end of the day, it's always easier said than done. Sorry, that's always the truth. Okay, and yeah, and so this company might talk about this packaging reliability, my part one. It's my perspective about dealing with this called CPI. Happy to talk. Hope you enjoyed it. Thank you very much. Bye.